So hi everyone, you can hear me, I guess? Can you hear me fine? Okay, perfect. I think we can just get started with the presentation. So thanks all for joining on this topic. My name is Hannes Weinmann. I'm the head of International Technical Center. And yeah, I would like to welcome you to this presentation, not only from my side, but also on behalf of Lead Intelligent Equipment. Very roughly regarding the agenda for today. So first, a very quick company introduction. Maybe some of you do not know Lead as a company. Then part two, we will talk about some major technological trends, especially solid state manufacturing. Part three will be about dry coating technologies because it's one enabling technology for solid state batteries. And then part four will just be a summary and some key takeaways. And I would also encourage you, if you have any questions in between, should not be a monologue here. So if you have any questions in between or comments, yeah, I would be happy to have a chat with you. So first, company introduction. This should not be like a commercial slot or something. I just want to give you a feeling how the company, it's a Chinese company, first of all. So how these companies are able to grow and scale. So actually Lead was founded in 1999. First product of Lead was a winding machine, but it was for the capacitor industry. And then Lead gradually expanded the business portfolio. And in 2008, which is not a very long time ago, first machine was for battery industry was a winding machine again. And then from 2008 until kind of 2016, they expanded the product portfolio. Yeah, I mean, up and downstream in the production line. So from the winding machine coming, electrode manufacturing equipment, calendaring machines, slitting machines, coating machines, and different parts of the assembly line. So different battery types. So cylindrical, prismatic, and pouch. And in 2016, they were acquiring a company from Zhuhai, Titans New Power. And this is a very important aspect because with the acquisition of this company, Lead was able to close the gap towards formation aging and able to provide turnkey solutions. And the turnkey solution is also put on the bottom right of the slide, 120 turnkey lines. This was actually one of the biggest enablers for global expansion for this from the Chinese market overseas, because the customers in Europe and also India or US, they weren't able to do the integration and all the equipment selection and specification at this time. But the demand for battery production was very huge. Yeah, and today we can see Lead is the largest supplier. So we sell about 10,000 equipments per year. We have a good market share for, I mean, in high-level products, so mostly consumer electronics and also automotive for more than 40%. Actually, in Europe, it's even larger. I would say it's more like 60 to 65%. And it's, I mean, if you have been to China, it's a huge battery production plant, several plants actually, 5 in China and one smaller one in Germany. And I mean, Lead is known for the battery production equipment, but actually they also have other business fields as automotive, fuel cell, photovoltaic. So if you have solar on your roof, the chances are pretty high that the solar panel actually comes from Lead automation equipment. And then there are certain cross technologies, so vision technology, MES technology, HEV, so everything that is related to intelligent logistics. So its own business units, and they apply the know-how of these business units into their different sectors. So which I think is a pretty good way to maximize the efficiency. And I mean, for the projects, for those of you who do not know, so I'm based in Europe. There's 13 projects in Europe, about the same amount of projects also in US. In Europe, it's mainly in the area of battery manufacturing. So I think what has been announced is like a CATL. We provide equipment for PowerCo, ACC, but also smaller factories. But we also provide maybe 30%, so 1/3 of it is actual module and pack. And for US, it's somehow also, it's more also tended towards consumer electronics. So if you have a Apple Watch, for example, and you think about the battery in this watch, or you have some AI glasses, then the chances are pretty high that these glasses or phone displays have been assembled by Lead equipment. And again, the enabler for these markets, especially for the European one, is the turnkey solution. For the how they expanded globally, I mean, outside from China, so they call it overseas, or we call it overseas. It's with the competence centers, and these competence centers, they are set up in Europe, they are set up in Asia and Malaysia, and also about to be set up in US. So they have parts of the center set up there. For Europe, I'm the head of the technological center. And what we do is we have staff to support the local regulations. So we do design reviews, we do design solution proposals. We try to make sure that the equipment that is designed and shipped fulfills all the norms and standards. Sounds pretty boring, I know, but there's quite a lot of work to do in this area. Then there's some pre-sales support or technical consulting support. So we have direct interactions with the customer, explain the technical solutions. Then we have also activities in the solution group. So that means we go on site with the projects. We do local trainings for machine operation, for maintenance, and we also dive into some new technologies like dry coating, dry mixing. And apart from this competence, there's also manufacturing capabilities for wear and spare parts mostly, and also some services for after-sales business, warehousing, and so forth. Okay, now to the interesting part of this presentation. It's about different innovative technologies. So we can see there's some, let's say, market demands or trends you will come across. So one of them is dry coating, one of them is solid state batteries, one of them is maybe sodium ion batteries. So it does not show any correlation on the time scale. It just shows what the hype curve kind of looked like. If it was like how overhyped it was before everybody kind of realized how difficult it is to implement. And you can also see that some of the hypes are actually linked to each other. For example, dry coating and solid state batteries, a lot of our customers, they think it at the same time. So when they think about new production plans or new pilot lines, they would consider two of the trends at the same time. And yes, and of course, even though you have these trends, for example, dry coating, I think it was not solid state technology was really hyped in maybe end of the 2018, 19, 20 was like announced for 2022 to be mass commercialized, but never really happened. And that was really quiet for a long time. And now it is again hyped, I would say, because the announcements and the prototypes you would see and what the manufacturers show, it comes more like towards an industrialization or industrialized product. For dry coating was never really overhyped, but we can really see that we have, I would say the equipment we manufacture is, a very sound state in the pilot stage, and we can really see that this dry coating technology will be part of the next gigafactories, at least for some of the production lines. However, if you have these technologies, there's a lot of challenges you have to overcome. So it's, for the dry coating, it's not just making the process happen, but also scaling the equipment and matching the production speed. So that's really challenging, and it kind of accounts for all these technologies. The reason why we have solid state batteries, so why do we want it? In the past, the focus was pretty much on increasing energy density. It was also because the structure in the cars, the way they were built, they did not allow a lot of room for batteries. So it was really important. In the beginning, it was kind of a bad compromise, I would say. They tried to integrate batteries into cars that were actually designed as being for the combustion car, and that's why the battery high energy density cells were needed. The way it was approached was on the cathode side with nickel-rich layered oxides, and on the anode side with a silicon-based anode. But however, this has been increased over the last decade. So higher nickel contents, higher silicon contents, but you can only come to a certain energy density. And if you want to go above, you need to switch the technology, which is for example, solid state technology. And in order to apply this technology, I mean, most efficiently to utilize the full potential, you have to have a lithium metal anode side. It does not make sense with some sort of a graphite blend. And for us, I mean, what we can see from the RFIs and RFQs, we would say that we see a commercialization for this technology maybe around 2030. For the reason why they excel, or why this technology excels, I mean, it's because of the energy density, as I have just explained on the slide before, but it's also good lithium metal compatibility. So if you want to use pure lithium metal anode, a solid technology is to be preferred because of the dendrite formation, how you can suppress that. If you do that right, you can also have a better safety, even though we have just heard on the panel that you will never have a battery that is, I mean, inherently safe. You also have good dimensional flexibility, so you can actually increase the size of the battery. You can have also a higher assembly yield, and you can have a quite high grading efficiency. For the process, or the overall investment, it's kind of like this. If you have a kind of a standardized production line and you switch different types of technologies, so for example, you go from your standard NMC chemistry towards sodium ion, you will find that the footprint of the gigafactory will be larger for the same amount of output. So if you want to make 1 gigawatt hour, let's say you need 25 machines or 28 machines, you will find that if you do sodium ion technology, instead of 28, you maybe need 50. So the footprint of the factory will be significantly larger. And also, of course, the amount of energy you will consume because you have just more equipment. On the other side, if you go from standard NMC chemistry towards chemistry with a higher energy density, footprint will be smaller and also energy consumption will be smaller. And this translates into more effects. So process complexity reduces. I mean, for solid state batteries, it's because there's no filling machine. But you also will have less logistics within your production line because you have less equipment. So there's less equipment you need to connect to each other. And that's also, it's a really big advantage actually, because logistics in a gigafactory is quite a complex topic. So you have various logistic systems, and you have also different independent parts, so it gets easier if you have less equipment. And if you have less equipment, also the labor demand will be decreased. You don't need so many operators, you don't need so much people to maintain all the equipment, and you can also have an improved automation rate, especially when you also switch the technology. There's, but the question is like, why don't we have this technology so far? Yeah, it's because there's certain pain points, and these pain points have to be resolved. We try to do that by having new equipment that we introduce to the market. For example, for the solid state electrode making, we will have machines for dry mixing, dry coating. For lithium metal anode making, we have new machines for calendering processes, intermittent lamination, for example, foil production. If you have some agglomeration topics with the electrolyte, there's new mixers introduced and new ways to feed the material. If it's about interfaces, there's ALD technology that can be applied to modify the interfaces. Porosity is also a problem because for isostatic pressing right now, it's like a discontinuous process, which needs to be continuous if you go into mass production. And there's also some inspection methods. So for your wet processing, you have kind of a quality assurance that goes along the process. And but for dry powders, you may not have that. And last point is production environment. So you will have a lithium metal anode. So also the requirements in terms of the production environment will change. This is just one overall process introduction. So if you do solid state battery production, you can still use your wet processing if you want. But you can also have a dry process, which goes well with solid state batteries. For lithium, for the anode side, so you have to change to lithium metal anode, which I have explained before. So you can have different processes there, like maybe lamination processes or hot melting processes or vapor depositioning processes. Then you need solid state electrolyte preparation. So the solid state electrolyte does not only go into the cathode, it also needs to be, there also needs to be a film applied on the cathode side, which is usually coated on a kind of a carrier foil and then transferred via a decal coating process onto the cathode. Then you can have some optional interface modification, and then you go in your kind of conventional cutting and stacking. But it is not, I mean, it's not just a copy paste for the cutting stacking machine, because lithium metal foil is kind of difficult to cut. And also once you have assembled the battery cell, you will find that it has a voltage. So you have to make sure that within your further processing, there will not be any short circuits that you will create with your intermediate product in your production line. After cutting stacking, you will need to isostatic press the different layers to establish the interfaces, and then you go into your assembly line, welding, punching, packaging. You will have also a formation process and degassing process, even though it's a solid state battery, and then you do your testing, grading, and inline inspection, kind of as you would do for your conventional battery. There are certain machines that we developed to facilitate the industrialization of these products. So this is a PVD machine, sputtering machine. So how it works is you have kind of a carrier film. It's usually some type of a polymer. You would unwind it, and then it goes around a very large drum, which is cooled, and then you do your vapor depositioning on this film. And you can rewind it. You can also go through this process multiple times, depending on how much thickness you want in this film. It's used for different types of foils. So I'm not sure if you know, but there's also some composite foils that are really popular in the Asian market. So you can have a foil that consists of two depositioned metal layers and like a polymer in between. It's to kind of enhance product safety. And after this process, when you have your very thin metal layer onto your foil, you can go to a depositioning machine. That means the foil will run through different baths, and you can deposition more of a metal onto the collector. But you need this initial layer to be able to conduct it electrically on the two sides. So it's kind of machines that enable you to have your different intermediate products that you need for the assembly. Okay, now into part 3. It's about aspects of the manufacturing. So when you look into the battery manufacturing, about roughly half the costs are in electrode manufacturing, half of the costs of the total manufacturing costs, and it's because you have certain cost drivers there. You can see that also the highlight is just for the coating, but actually electrode manufacturing goes also into calendering and slitting, and some even consider the notching as being part of the electrode manufacturing. So there's quite a lot of machines involved into it. And there's cost drivers, for example, coating machines. They tend to be really long, maybe 100 meters. They are more than, multi-million euro-dollar machines. You also will have some large drying ovens, and you need your solvent recovery to get back your, for example, your NMP. And these processes tend also to be very consuming a lot of energy, so energy intensive. Also, about roughly half of the costs for the solvent recovery and for the drying. So the solvent you will put into it in your wet coating, you need to evaporate, you need to heat it up. So water to about 100 degrees, NMP to more than 200 degrees, 202, to be able to evaporate it. And these kind of costs add on into your manufacturing, and that's one motivation to also change the way the electrode production is designed process-wise. For the electrode production, one motivation is to go from a wet to a dry process, but at the same time, you need to ensure that the properties are the same, because electrode design actually plays a very critical role in the way your battery will perform later on. What is really important is the control over the structure of the electrode active material, so how it is formed on a microscopic scale, and also how it will perform later on. And there's different variables that need to be controlled. For example, it's how uniform the binder is distributed, how well the porosity is controlled, how dense your material is. This is kind of how the performance parameters in terms of electrochemical performance and also, I mean, mechanical performance are kind of influenced. And then there's also some key factors that drive the dry coating implementation. We have had a different picture before for the solid state batteries. Sometimes it's the same motivation. Dry coating also is small footprint. The reason for this is because actually certain process steps are integrated into one machine. So in a dry coating machine, you typically will find a mixing machine or some sort of a pre-mixing machine. You will find your film forming step. You will find a lamination step. You will find a calendering step, and you can also find maybe slitting in there. So there's a lot of machines integrated into one machine, which is kind of per se a benefit. Energy consumption will be way less because the formulation is dry, so there's no solvent that you need to evaporate. And the potential ROI is also faster because the investment in the equipment is smaller, but also the running costs you will have when operating it. For the complexity, process is simplified. It's simplified because of the integration, so you don't need to link all the machines together. Every time you have a machine and you need to transfer the product from one machine to the other machine, you will have like a start and the end of your material roll, for example, that you need to waste, and there's some transport involved where something can go wrong, and yeah, so it simplification by reducing the amount of machines. So complexity is reduced. Yield is usually increased because of the integration and the different interfaces you avoid. Yield is usually up. And also there's no solvent recovery for dry coating processes. So solvent recovery is also quite a big equipment or machine in this sense. Electrode design, it supports next-gen materials. For example, a next-gen material would be the materials for solid-state battery in the product, but it's also beneficial in terms of the mechanical robustness. So for example, if you have a dry coating processes with a kind of film formation process, when you have a film formation and a fibrillation process, it's kind of a reinforced fiber part that you would also create in other industries. So the mechanical properties of the electrode could be really good. And therefore also it kind of translates into the performance also. So stability, cycle stability, energy density might be improved because there's less porosity and electrochemical performance. And then there are certain techniques. So basically, when we talk about dry coating, it always consists of three parts. One part is mixing, one part is the actual depositioning method, and the third part is the pressing. And how these technologies differentiate is basically by the second part. So how the layer is depositioned, so how the material is depositioned on the collector. It's shown on the bottom left, so dry coating methods. And you see some of them are larger bubbles, some are smaller bubbles. So the larger ones are the ones that are more advanced. So for this presentation, it's hot melt extrusion and polymer fibrillation. And of course, depending on which one you choose, it will also have impact on your material properties, but also on the complexity and the process. Some more details for the mixing. So when you have a dry mixing process, it's actually considering different steps as the wet mixing process as well. So you have a pre-mixing stage, you have a fibrillation stage, and a granulation stage. So for those of you not familiar with these names, pre-mixing is kind of with the conventional mixing as well. You kind of try to distribute your conductive agents around your active material particles. This could be considered premixing. Fibrillation is actually making the binder form kind of a web-like structure. and then the mass is really sticky, and then you try to granulate it again to be able to transport it. So the way it is usually done is that um, there's different process windows for this fibrillation. So fibrillation is kind of dependent on the shear, but also on the temperature. So you want to heat it up a little bit for the fibrillation to kind of enhance the process step. And then at a certain step, you want to cool it down again to make it more granular again. And the way you can cool it down is either by the side of the mixing barrel, or you can also introduce like a liquid gas into it, for example, nitrogen, to cool it directly. And the reason why it needs to be granulated is because the feeding of the powder is really tricky to from your mixer to your film forming station. So often you would use belts simply to feed it. You can also use some special piping with anti-stick coating inside. You can also introduce like vibration to minimize the contact that you have between your powder and your equipment walls, so to say. But it needs to be cool. And yeah, after mixing, you would have the second part. So it would be, for example, a hot melt extrusion. Hot melt extrusion is also used by some large automotive companies that make batteries. So it's a really dense and smooth electrode. It has a good stability and a low porosity, typically, a good adhesion to the collector, and a high uniformity in thickness. It's because I mean, the hot melt extrusion is also used in other industries and in general a well-controllable process. The downside of it is that the amount of polymer you need is typically high. I mean, higher than for fibrillation, because otherwise you cannot get your material through your die. And also these, I mean, there's some problems with the die itself that if you press your material through the die will heat up and you will have maybe some effects from this heat in the die. However, for this process, you would need a thermoplastic binder to be able to extrude it. And then you have to kind of bond it with a metal collector by roll pressing or hot pressing, whatever you select. The second option for the second part is the fibrillation process. So you can do some pre-fibrillation in your mixing already, but the main fibrillation step is when you form the film. Usually, I mean, you need a binder that can be fibrillated, which is typically PTFE or some material that is kind of derived from it. It has a moderate to high porosity, good uniformity. I mean, good uniformity in the term of how you can control the fibrillation. Fibrillation is also kind of a random process, so there might be local inhomogeneities, but on a microscopic scale. It has a very good mechanical, resilient, and flexible characteristic, and there's a low binder content possible. The downside of it is a moderate adhesion to the collector. And then the third step, actually the picture is not showing only the third step, it shows somehow an integration, but it's kind of a lamination machine. So when you laminate it, usually after lamination, there's also one more step, which is a kind of a calendering step. So it's not just binding the film to the collector. It's, I mean, also for the conventional battery production, the calendering step is also used not to just decrease porosity, but also to kind of make a connection between your particle and your foil. So you push the particle physically in your foil and increase the contact points between it. Yeah, and then for the electrode manufacturing, so for the wet processing, you have like your rheometer, and you can put your slurry there, and you can, you have your quality assurance methods. But for the dry electrode manufacturing, it's a little bit different. It's kind of in a lab and pilot stage. So what you can do, these are some pictures from the labs, from our lab. So you can have take a look at the color. If it's uniform, you can maybe see how it feels like when you go through it with your hand, if it's resistant, or you can maybe press it into a form, or you form a ball or something like this. So, but it's not really a scientific testing method. So it relies more on experience of the process engineer or operator who operates the machine, and it's not really good for quantification or optimization of the process. So Lead is typically a company that does not any. I mean, our capability is not developing testing equipment, but for this case we did. There's in Shanghai, there's the Lead Academy. Most of the people who work there are PhDs actually from the university close by, and they have developed like a testing equipment that can do the characterization of these powders. And there's different kind of the characterization. What you can do in this machine kind of simulates the process you will have later on. Yeah, in terms of how the powder flows, how the wall friction is, tensile tests, compression curves, etc. And these are some graphs. It's not like a general. I mean, it's not a general rule I'm showing here. It's just some examples from this machine. What you can find, for example, for your shear stress, is that the shear stress increases if you increase kind of the pressure. So you see the influence of the pressure. The higher the pressure, the higher the shear stress will be. You can see the influence of the degree of fibrillation on the top right. So when you do a pre-structuring, your shear stress will be higher. You can see the influence of the material. So LFP and NMC, they have a very high shear stress. But if you look at graphite, because of its layered structure, shear stress will be lower. And you can also see the influence of the shear rate. So if you increase the shear stress, so in degrees per second, it tends to get like in a fluid kind of like behavior on the top and on the bottom right figure. Yeah, and now some summary and key takeaways. So what we have talked about was the motivation for different technological trends. You can also see that some of these trends kind of go together, at least from the process development side, and also how the customer think about it. I have shown you some ways to make the different products. I've also shown you some equipment from our side that we developed to kind of facilitate the industrialization of these technologies. For solid state batteries, it's important to control interfaces and mechanical stability. So by choosing, for example, the right method for the dry coating mechanism, it's also very important to integrate material development with equipment development. So you would maybe call this a co-design process between product development and process development. Flexibility is also really critical to our clients. So they usually require equipment that is highly flexible in terms of the materials they want to produce, because the technological route might not be very certain. Cost savings are also essential, especially for the new markets. They kind of try to skip the standard production processes and go directly towards a new production mechanism to reduce the costs. And dry coating especially is a very promising technology because it has a lot of benefits in terms of lowering energy consumption and reducing process steps. So I hope you have liked the presentation. If you have any questions, I would be happy to go into discussion with you. And yeah, thanks again for joining this.